Okay. Yep. So I'm Salif Ali Mirza. I'm from University of Tennessee, and we are representing this advancing power magnetic materials modeling through attention-based unit with linear conditioning. So let me briefly go through our method. So our method is actually a four-stage method, and we utilized unit based architecture to model the complex relationship in magnetic materials, and we addressed limited data availability, what is the challenge you gave us with a 1D generative adversarial network. And also we enhanced our model's capability using metadata, and in those metadata we are utilizing the waveform type and the frequency and the temperature. And we have implemented a attention mechanism in the unit model to improve the focus and adaptability to complex sequence to sequence task. And in our third stage, we have actually implemented a concept called noisy supervision, which is actually a semi-supervised learning method, which enables us to model efficiently on both labeled training data and unlabeled test data. So we wanted to improve our model's performance on the unlabeled test data, but without knowing the labels. And also we applied a knowledge distillation to transfer our learning from a larger unit model to a smaller and more computationally efficient counterpart. So let me go through step by step of our method. So first we have like a data augmentation stage. So our aim was to use a unit model for their sequence-to-sequence generation capability, but we found out that unit models face overfitting challenges with limited training data. So we used a conditional 1D generative adversarial network to generate few synthetic data, enhancing the dataset's size and diversity. And we used a conditional 1D GAN because we had different waveforms types. So with the condition, we can actually generate precise waveforms like sinusoidal wave or a triangular wave or a trapezoidal wave. And during the training of GAN, we actually concatenated our B signal, H signal, frequency, and temperature into a single vector. In the second stage, we call it a pre-training stage. In pre-training stage, we train the unit model on a normalized augmented dataset. And we use frequency, temperature, and the waveform type as a metadata. How we are using a metadata, I'll explain in my next slides. And also the type of input signal, like the B signal, how we are actually determining the B signal. So we used second derivative. We analyzed the second derivative of the B signals to get the waveform type. And this is actually our unit network. So you can see it's a hefty unit network. We have used GRU layers and also a affine transformation layers. So we use this metadata like frequency, temperature, and waveforms to generate two parameters, gamma and beta, which we feed into the affine transformation layers. This actually helps us improve the model's generalization capability based on the waveform type and also based on the frequency and temperature variations. And we added an attention layer in middle of the unit network to improve our focus on the important features, aiding the complex sequence-to-sequence task. In our third stage, we call it a self-training stage. Why we call it a self-training stage? Because we have like, we previously trained on our training data set, but now we want to improve our model's generalization capability on the unseen data. So we used a concept called noisy supervision, which is a semi-supervised learning, and this uses both the labeled and unlabeled data set. To do that, we take the model from the second stage and we generate schedule labels for the test data set. In this case, schedule labels are actually the schedule age signals for the test data set. And initially, we select only the instances that has low training loss. And we employed a dynamic approach to adjust the fraction of the schedule data set we will utilize to train our model in each epoch. And we use this clean instance selection to select uh, the samples that has the lowest loss. So we bargain that if we generate a schedule age signal, then the model will have a lowest loss on those if the schedule signal is close to the original label. And the model, this model is actually fine-tuned on this augmented data set, where the augmented data set contains the test data set with a schedule label and the clean data set. And finally, we use knowledge distillation to transfer the insights of the fine-tuned unit to a smaller unit, because we found out that it's really hard to train a smaller unit on limited data. So what we did is we increased the model parameters, model size to better generalize over the small data sets. And then we actually transferred the knowledge from the big network to a smaller network. So what kind of challenges we encountered? So first of all, we selected a unit architecture which is renowned for its effectiveness in sequence-to-sequence task. But the problem with the unit network is they are pretty, they need extensive training data to get a better generalization. So to solve this problem, we used a 1D GAN network to augment our data set. And another obstacle we found that manageable model size, because we wanted to keep our model size smaller so that we can employ it in a edge network, but smaller units does not have a good generalization capability on smaller data sets. So that's why we needed to train a larger unit and use the knowledge distillation to compress the unit's knowledge into a smaller model. What we learned from this challenge, apart from that this is a really hard challenge to solve as an CS background. So we gained deeper understanding in intricacies on modeling magnetic materials, acknowledging the complexities of accurately representing their properties and behavior. We also enhanced understanding how to incorporate domain-specific knowledges like magnetic properties or waveform types. And these domain-specific knowledges are crucial for any reliable model's accuracy or performance. Personally, I also acquired knowledge about this semi-supervised learning approach, where we can use the labeled and unlabeled data to improve model's generalization to unseen data set, and also recognize the need to balance the model's complexity and computational efficiency, especially in power magnetic materials modeling, where high performance model must be deployed in a smaller edge devices. So that's all from my side. That's all in my presentation.
Great. Yeah, great. Thank you. Thank you, Said. It's very, very good presentation. And sounds like you come from a computer science background.
Yes.
That's great. Yeah, so one of the purpose here is that we want to create a problem, lower the bar for a student or faculty or researcher from computer science environment to understand the challenges we're facing, and really leveraging the most advanced tools that you guys have already developed to solve our problems. So yeah, welcome to the community. And I really like this GAN approach, which ties back to the K.O. Leuven's approach. And I guess you guys can probably collaborate.
Yeah.
And yeah, so I would say this approach is really powerful, can offer a lot of possibility beyond what MagNet Challenge is designed for. Like, we are designing from the power electronics perspective, but there are a lot of other functions that this type of model, generative model, advisory model can offer, but we were not testing it here. So I definitely were very excited about this approach, and encourage you guys to keep exploring the possibilities.
Thank you, Dr. Chen.
Yeah. Yeah. So any questions from the audiences? Comments?
Yeah, so thanks for the presentation. It's very, very good work here, and especially a lot of like computer science techniques used here to improve the quality of this work. And especially, I think it's a good practice to do just like you did. Firstly, you train a big model, and then you use the knowledge distillation to further reduce the size of the model, rather than you train a small network from scratch. So I was wondering what kind of algorithm did you use for this knowledge distillation, distillation to, yeah.
It's like a student-teacher method. So where a bigger model actually predicts a label for the smaller model, and a smaller model tries to predict those the output of the bigger training model, and we reduce the loss between those predicted from the teacher and the students.
I see. So how much to what kind of ratio did you reduce the model size from the previous one to the smaller one?
I believe when we trained our teacher network for most of the materials, it was over 100K parameters, but our final models were like in range of 25,000 to 32,000 parameters.
That's pretty good. So I suppose the accuracy is not much effective by doing this.
Yeah, it will affect a few much, but it's literally negligible based on if you think about like we are reducing the model size to 1/4.
Yeah, that's true. Thank you.
So what's the rationale behind UNet? Like I was not a computer science background, so I didn't know what's the benefits and advantages of UNet.
So UNet is actually like really good for sequence to sequence generation. So you know that we had a B signal and we need to compute the H signal. Both of them are actually a sequence. So UNets are really good with sequence to sequence generator.
Okay. What's the feature behind it? It's like it's tying. Why is it called a U? It's because you're tying.
So you can see this this network, like it started as same and finishes as same. So it's like a U.
I see. So it's sort of like a transformer, modified transformer type of model.
UNet is actually
it's different.
It's different. It's different. It's different.
Okay. So it's just different from LSTM or transform. It's a different type of network.
LSTM is actually like we can use LSTM inside a UNet. UNet is actually an architecture, not like a method.
Okay. Understand. Yeah, so I would highly encourage you to look at all the other models that were developed by our community, and then see if there are ways of better tools from computer science we can borrow.
Yeah, sure.
While tying with better physical understanding.
Sure.
Yep. Great.
So, thank you, everyone.
Yeah. Thanks, Shai. Any question? No. Okay. Then let's move on to our next team. Fuzhou University from China.
Okay.